So this is just a summarization of what we're going to do, and we'll start with day one. I think everybody has got this information over your email, the web page as well as the Git page where we'll be updating all the material, any README, PPT, everything will be there on this Git page. So yeah. Okay, this session will be taken by 4 of us. I'll be dealing with the first half of the session, where I'll be talking about the concepts in networking. I'll be there for the second half, but the students around here at IIITD will be taking care of the hands-on session. Sumit, Nazia and Mariam. And this is the outline of my talk. So the first part, which is the theoretical session, I will be talking about the Linux networking stack, how the packet moves from the time the packet is received at the network card up to the time the packet is sent out of the network card. So we'll look at the entire journey. Then after that, so first we'll just talk about traditional how things work. Then we talk about how the network cards have been evolved over a period. And after that, we'll also see how the network packet processors with software as well have evolved over a period. So that will be the end part of my session. Before I start, I just want to see that what is the knowledge about computer networks you guys have. So typically in your, okay, how many of you are BTech folks? Okay, and I'm assuming everybody has studied computer networks already. How many of you are MTechs? Okay, great. And PhDs? Higher hands. Okay, thank you. So everybody has already learned computer networks, and this picture is like kind of imprinted from all theoretical books and everywhere. So can you help me out? If you want to send a TCP packet from the sender on your left hand side up to the receiver on the right hand side, you also see those 5 layers on there, starting from application layer up to the link layer, and then you have your NIC drivers and your hardware NIC. So can anybody tell me how will the packet move from the sender to the receiver?
The data packet will start from the application layer from the sender side and to the transport and network, data link, and through the hardware they will communicate with this receiver, and then they will reverse back to the application layer where the request will be sent.
Great. Yes. So, what's your name?
Pratham.
Yeah, I think it's better that everybody call out their names also, so that way we learn each other's names also and network. Yeah. So Pratham said, which is exactly right. Your packet will be starting from the application at the source, at the sender, and via the physical layer, which could be wires, wireless, anything. The data will be reaching up to the receiver. Obviously, I've drawn a simple wire there in between. There could be some routers, switches, etc. also. And at the receiver end, the data goes from the hardware up to the application. Now my question is here. I can see this green colored picture here where you have the stack. Where does this exist? At the kernel? Is everything within the kernel? From the transport layer. Okay, good. So from the transport layer up to the data link layer, is that right? Okay, no. Driver is where? Kernel module. Okay, so that picture can be a little bit incorrect to show. So let's have a correct picture of this. So, okay, let's start from here. You've written an application. In your assignment, you must have written a socket programming application. So you wrote an application, and your intention is this. You have a hardware network card there, and on this card there are 2 queues. You can see 2 rectangles there. These are packet queues where the incoming packets, the transmit and the received packets will be coming in and stored there. So you have your hardware and the application. Application is running in the user space. You have to write an application for communicating with the NIC. What do you do? I have already said it's an assignment of your networks, which is socket programming. So what do you do?
In the socket
create a socket. So what is a socket? Is it something that resides in the user space, in the kernel space, nowhere, in the air? What is it?
It's basically a file descriptor to write from a particular memory for dedicated to a particular code.
Okay, so you're right. So when you say a socket, exactly what it is?
It's a file descriptor.
It's a file descriptor or it's an interface? It's an interface. So when you say that you are creating a socket, so basically it's an interface which communicates with your TCP/IP stack, or you call it as a network stack. So it's an interface, and this interface is between the user and the kernel. How can I create a socket? So you can see that the green color thing is the user space. This is the kernel. How can we create a socket? You have an interface, a library there. How do you move from user space to kernel space? System call. So the way to, when you create a socket, when you use those interfaces, APIs, for creating socket, reading from a socket, writing into a socket, that means sending data, receiving data, you basically are making system calls. So you make a system call to connect to and communicate with the kernel. And those layers that we were talking about, they exist as a form of the TCP/IP stack. So those layers are nothing but software modules that talk to each other, and they are part of the kernel. And this stack talks to the network driver, because each and every network card will have a different way of, different language. They'll be speaking different languages. So that language is known by these drivers. So this, and they expose common APIs. So using the common APIs, the stack talks to the driver and the driver talks to the hardware. So this is just a simple cartoon diagram of how your machine looks like internally. Now let's start with the journey. Any questions here? Okay. So let's start with the journey of a packet through the Linux network stack. So we'll start with the receive path first. So before I start with the actual journey, I want to clarify a few things here. So when a packet comes in here, okay, so when a packet comes in to your NIC, what's the first thing that happens is you have two queues at the network card, that is your TX queue and the RX queue. So if the packet is coming in, it will enter into this RX queue. So I want to just describe what this RX queue is about. And before even we go there, when you start up your system, there will be, you must be aware that a driver, every hardware will have some driver memory, some hardware memory, and this hardware memory is located where? What are the types of memories that we have? We have RAM, we have disks. So where is this driver memory located? Is it in the RAM or the disk? It's in the RAM. Now when we talk about driver memory, these driver memory pages are pinned into the memory, and it's been told specifically to the kernel that these pages should not be ever moved out of the RAM. This concept is called as pinning. So when you boot up your system, there is a memory area specifically for the networking stack, and this is the memory area that you see. This memory area is the place where your packets are stored, and this memory area is pinned. Nobody is going to remove this out from your memory. Data is copied into these packet buffers. And how does this copy happen? Acceleration solution for this memory copy, and that acceleration solution is the DMA, where DMA stands for direct memory access. So basically, what is the input to a DMA? There are two inputs to a DMA. We specify the address from where you want to do a copy. So two addresses, source address copy कहाँ से करना है, destination address to where you want to copy, and the length of how many bytes you want to copy. So these are the three parameters that we need to specify. And what exactly, now coming back, so I think any questions about a DMA? So DMA is a hardware mechanism for copying without using the CPU. Now when a packet comes in, what exactly happens is, this packet, there are three things that are stored about this packet. What are the three things? As I told you earlier, the source address, where the packet is stored, the destination, the source address, the destination address, and the length is what is needed to the DMA. So DMA does this operation, pushes the data into the packet buffer, and in these network queue, this queue that you see, the RX queue that you see, what is stored is the address of where this data is stored plus the length of this particular data. So once again, what happens when a packet comes in? First step, DMA the packet into the RAM, which is a pinned memory, and make an entry into these queues, RX queue, about the address and the length. So we maintain a circular queue or a circular buffer for both transmit packets as well as for received packets. And this queue is shared between the network card, that's the hardware, and the NIC driver. So your kernel has access to this queue and the NIC has the access to this queue. Once this is done, what does the NIC do? Once this operation is done, there is an matching of the destination address, the MAC address, and checksum verification is done if the data has arrived correctly or not. And these packets, after they are DMA'd and when the ring buffer is initialized, an interrupt is triggered by the NIC. That's a hardware interrupt. And after this hardware interrupt, typically a hardware interrupt is a high priority interrupt. You have to take care of it. So CPU must be running some other program. CPU will be switched out and this hardware interrupt has to be handled. But network start processing is a time consuming process and we can't waste CPU cycles from the application that was already running there. So we divide the interrupt processing into two parts, top half and bottom half. So in case of top half, we do minimal processing that is needed and do all the heavy lifting exercises in the bottom half. So what exactly happens in the top half? And create a soft IRQ and basically create a schedule saying that after this, the next set of processing will be done within the after some time later, and this particular process is created and scheduled for later. This process is called as the soft IRQ or soft interrupt processing. Now whenever the CPU becomes available, it interrupts and okay, I have talked about this top half processing. So top half processing, it is again interrupt processing where switching will happen, and this is the typical way processing happens. You will look up for the system call. So we know it's a syscall. So there will be a syscall. You look up in your IDT, interrupt descriptor table. You call the interrupt service routines, acknowledge this interrupt and schedule the processing for bottom half and switch back to user space to continue with your application work. Now, when the bottom half processing starts, you switch back again from the user space because application was already running to the kernel space now, and then we do something else. So before we go for a break, I just want to give you a big picture of what we do before doing bottom half processing. So driver allocates something called as a network structure, which is called as skbuff. And this is dynamic allocation. This is the most important structure in Linux networking subsystem. Why? Let us understand what this skbuff is. So it's an in-memory structure that does not contain packet data, but it contains packet metadata. And what is the metadata that it contains? Let's take this example and see. So it's an in-memory dynamically allocated structure. If this is your data packet, in this picture, where is the data packet stored? Data packet arrived at the NIC. It is stored in the packet buffer. And what does this TX and RX, what does this ring buffer contain? Addresses. So these are just the descriptors. These are the addresses plus the length. So they point to these packet buffers. They don't store the packet. The packet is stored in the device memory, which is pinned memory. Now, for example, let's take an example. Everybody has used some kind of a packet capture tool like a TCP dump, Wireshark, something like that. I think everybody must have looked at some such tool, right? So if that tool wants to filter out packets, right? You want to only look at, for example, just the TCP packets or something like that. So how does the tool work, and how does it work so fast? So all the network packets that are arrived or we are sending, every packet has a one-to-one mapping with a structure called as escape buff. This escape buff contains metadata about the packet. I have just shown a limited items or fields in this escape buff. The number of fields are huge. Like there are many fields, and with every Linux version that comes, these fields keep changing. So you can see the first field that you see is an interface, which specifies this packet is coming from which interface or has to go to which interface, the data about that. Protocol, it's a duplicated information. Protocol is present in your packet headers also, but you also have this extra information saying that what protocol packet is this. That's the reason if you're taking TCP dump or Wireshark filter for only TCP packets, you'll just look into the protocol field and filter them. You don't have to parse and see whether this is a TCP or a UDP or an ICMP packet. So escape buff helps you in doing those filtering. Then you have a several set of pointers over here. Now what do these pointers do? This row that you see, this row is nothing but your device memory where your packet data is stored. And when you initially allocated this device memory, but your packet size can be of variable size. So you allocate some max size in the memory, and that's the reason you will have some empty spaces at the start and empty spaces at the end. And this packet memory can grow over a period. So what do I mean by can grow? I got a packet which was an Ethernet packet. I hope, do I have to explain that packet has got these headers of TCP? So you have your packet data. It will have a transport layer header, which is a TCP header, a network layer header, which is an IP header, and your Ethernet header. Any questions here that how this data packet looks like? No questions here, right? Okay. So a packet has been stored over here, which came from the network card. Now, what if you want to modify this packet here itself? And for example, what if I want to add an additional header? It was an IP packet. I want to push this IP packet within another IP packet. This term is also called as IP and IP encapsulation. So then what I want to do is I'll have to take this particular part of the packet. I would want to push this Ethernet header to the left and push one IP header in between. So if I want to do something like this, I need some space to grow towards the left hand side, as well as I may need some space to grow towards the right hand side, and that's the reason there is some empty space kept. Then you may have some questions here. Do you have? How much empty space is good enough? Huh? Who decides the empty space? Yes. So who decides the empty space? It will be a configuration parameter. But yeah, that's right. It will be a configuration parameter. But can there be a case where you want your packet to grow further, but there is no empty space? And if that's the case, you will have to take this packet from here and make another copy of this packet, which will be a compute intensive task. So basically the design of your system decides the performance of your system. So how you decide, because there is always a trade-off. As you correctly said, there will be a trade-off. What is a good enough empty space versus what is the performance that you want? So if you keep large empty spaces, you will use a lot of memory. If you use small empty spaces, you will do a lot of copies. So it's performance versus How flexible is your design? Okay. So yeah, as I already said, you'll have to do a copy if the packet grows beyond this. But if the packet does not grow beyond this, there is a chance that you don't even have to take this packet up to the application layer. You can do some modification here itself and send the packet out. Here matlab here kya hai? What is this? Do the modifications here means what? At the packet buffer means we are where is the application running? Is it a user space application? The application is running within the kernel. Because only, if you remember, who has access to this packet memory? The NIC driver and the NIC. So if you can modify a packet within the kernel itself, you can do that directly in this packet buffer and send the packet out. Okay, so yeah, so now just coming back to the skbuff, you have multiple pointers. I've shown a few of them here. So the head pointer actually points to the start of the skbuff allocation. The end pointer points to the end of the skbuff allocation. The data pointer points to the start of the actual data. So in this case, your actual data, it's an Ethernet frame. So it starts at the Ethernet header. So it's an offset to the Ethernet, the pointer to the Ethernet header. And the tail pointer points to the end of the data. So what can be a case when you want to push data, when you want to push something after this data? So every Ethernet packet has the checksum at the end of the Ethernet packet, right? I don't show it, I'm just showing data. There is no checksum here. Any idea why that's not there? So when I explained the NIC processing, I told you that during the NIC processing, when the NIC receives the packet, today all NICs, every NIC in the market, any NIC you pick up, will do this checksum validation within the hardware itself. So the checksum is checked within the NIC itself and it never moves up to your device memory. It's already removed and moved up to the device memory. So you don't have the checksum here. But if you want to modify this packet and send it out, will you have to add a checksum field there? You may have to add it. So there are two ways, either you do it in software or hardware. If you want to do it in software, then your right hand side will grow after the data part. So you need provision for both these sides. There could be other reasons, I'm giving you one example. There could be other reason where the right side could grow. Okay, now why is this structure so popular and why is it important? So what are the advantages of doing this? So let's say your application, you have two kernel applications. Both of them want to use this particular packet. Let's say you have opened up two processes for TCP dump and let's say some other, let's say two TCP dump applications, and they are listening to different interfaces. Let's say that. So both of them are actually looking into this packet data. They're looking into this same packet, for example, this possibility. So if that's the case, will we have to have two copies of this packet? Or a single packet is enough? A single copy is enough? So the answer to this is a single copy is enough. Okay, to give you a better example, maybe TCP dump example doesn't fly through you, but you know that your packet is processed by, first it will be processed by your link layer, then the network layer, then the transport layer. So every module is accessing this packet. Now when every module is accessing the packet, you'll have to pass this packet from one module to the other. So to pass this packet, you may have to create a copy of this packet. Do we want to do that? It's not going to be, it is bad. It's not going to give you performance. So you don't create a packet. What you do is, you just pass on this skbuff struct, which is carrying the metadata about the whole packet. Second thing, I was talking about TCP dump, T-Shark or something running in parallel. They want a copy of the same packet. So instead of creating two or more copies of the same packet, a better idea would be you just create copies of this skbuff structure. So there will be two copies of this structure, and both of them will point to the same packet. let's take a few advantages examples here. I talked about we are moving this packet from the driver up to the network layer. So if we push it to the network layer, we would want to remove this Ethernet header from here. So instead of if I want to remove it, matlab kya? I'll have to copy this packet and just copy the IP header to data part. So instead, what is done is, for efficient removal of packet header, you just move your data pointer. So now escape buff is pointing to this. Data is not lost. Data still exists, only the pointer has changed. Similarly, if you want to send this packet to the transport layer, TCP layer, you just move the pointer and just pass the escape buff structure. That's going to give you performance. So that's one advantage of using escape buff. Second advantage, as I talked about, encapsulation. You may want to add an additional header in between. What you need to do is just move the pointer ahead. And if I don't even talk about encapsulation, if I'm sending a packet, I want to add a IP header to this TCP packet. What I have to do is just move the header pointer. So this data pointer will start pointing from TCP offset to IP offset. So it's efficient to add additional headers. It's efficient to remove headers. And second, the third case is cloning. As I said, there are two applications who are having copy of the same packet. Both these applications will be pointing to the same packet. You can see, you don't have to create a copy. What's the challenge here?
Other process tries to write something into the packet.
Yes. So if other process tries to write something to the packet, you can't write. So if there is a write operation, you'll have to create a new copy of this packet. So that time copying process has to be done, otherwise you will not have to do it. So the advantages of escape buff are enough to use it for the networking subsystem. And what is the problem? As we said earlier also, one of the problem, you can't write packet data. You can only read if there is cloning. If the borders exceed, you will have to allocate new memory, do the copy business. So there are a couple of such disadvantages. So this was about what escape buff structure is. There are many other pointers that exist in this escape buff structure. For example, we were only pointing to the start and the end of the data packet. If you want to provide pointers for start of the Ethernet header, start of the network header, transport header, you have pointers to them also, pointers to start of data. And remember, data is never lost. That means if your application is viewing this as a TCP packet, if you want to view the same packet as an IP packet, one application can view this as a TCP packet. It will look from this pointer, transport header pointer till the end. Another application can have a view from the IP header to the data packet. That means from here to here. So the point is, there can be two or more applications having different views of the same packet. Yeah, so I think let's take a break. I've explained escape buff. After the break, we'll look at bottom half processing completely. DMA, where? Packet buffer. Where is this packet buffer? In the RAM. Next, in the RX queue of the NIC, you will add the address and the length, which will be pointing here. Done. After this, DMA's job is done. No CPU involved, nothing at all. Next, after this is done, it's a hardware interrupt. Hardware interrupt, so CPU has to stop whatever it is working on and handle the interrupt. Handling the interrupt implies syscall, do the hardware interrupt processing, come back. Hardware interrupt processing involves just telling the NIC, shut up, I have seen your packet. Schedule a new process for the rest of the processing, and such kind of a process is called as a soft IRQ, a software interrupt. It's scheduled, put it into the ready queue, job is done, top half ka, and CPU again switches back from the kernel space to the user space. Syscall khatam ho gaya. CPU will continue with its regular application processing. And whenever the turn of this software IRQ comes, whenever the CPU becomes available, it will start processing the software interrupt. That is where we were talking about the bottom half processing. So till now whatever I have talked about is DMA and interrupt and top half processing. So this is just a summarization of what we did. Let's continue with the soft IRQ. So the first step in bottom half processing is allocating this escape buffer structure. So throughout the entire Linux kernel, there are two structures that are used. One is the escape buffer structure and the second structure is a sock structure. This sock structure is a corresponding structure of the socket interface that you talked in the user space. So apart from this, no other structures are needed in the Linux kernel for handling a packet. Okay, let's move forward. Yes, so bottom half processing, after this escape buffer allocation is done, which the driver does, it's a dynamic allocation and that means it will be stored in the heap memory, and this escape buffer is updated with the packet metadata. We saw what the metadata was. The Ethernet header is removed because the first layer processing that you do is the link layer processing. So Ethernet header is removed, and removed ka matlab kya? Can you help me out? Just change the pointer, that's it, and pass this escape buffer to the network stack. So now when I talk about, so all this job till here is done by whom? By the NIC driver. And after this, the network stack implies the first layer, which is your internet protocol module. So because I'm talking about a TCP IP packet. So internet protocol module, that particular layer 3, whatever module it is, that protocol handler is invoked. And what is passed to this module is the escape buffer pointer for the packet. We are talking about bottom half processing right now. Everything is working currently in the kernel space. So what does the layer 3 and layer 4 processing involve? The common processing that both the layers do is matching the destination addresses, verifying the checksum. Now this checksum, remember, is not the Ethernet checksum, it is the IP or the TCP checksum. And removing the header. Again, removing the header means changing the pointer. So again, packet abhi ek hi jagah pe pada hua hai, DMA ne ek jagah pe dala hai. Specifically, what does layer 3 do? It does route lookups. This particular component of layer 3 processing, we'll be looking in the hands-on session where we will be building network functions. There we will see that how does this routing happen, how can we build a firewall, how can we build load balancers, all of that based on layer 3 processing. So this will be expanded further in the hands-on session. But rough overview, routing lookup is done. If there were some fragments that were arrived, you will have to combine those fragments and pass on this for layer 4 processing. That means TCP module will be invoked. Specific to layer 4, now what exactly happens? Just let's move back to our application. Whenever a client or a server application was created, the first thing what you do for communication over the network is you create a socket. So when you make a socket system call, there are 2 queues for each socket that are created within the kernel space. There are more than these also, but right now I'm only talking about the 2 queues, a write queue and a read queue. So for every socket that you create, there is a write and a read queue, and a descriptor is passed back, and so whenever you want to refer to these queues of that particular socket, you'll be using that descriptor, which is returned when you create a socket. So your sock FD is this one. Now, we were talking about layer 4 processing. So what does TCP do? It handles a TCP state machine. So can anybody tell me, is TCP connection oriented or connectionless? Connection oriented, which implies there is a first part where you can establish a connection between the 2 endpoints, after which you start sending data. So, and I hope everybody remembers that you have this 3-way handshake where you have SYN, SYNAC, ACK processing that is done. So this handling of TCP state machine is never done by the application, it is managed directly within the kernel space. And who does it? The TCP module in the kernel. So it does this handling of the handshake. Only when the data arrives, that data is forwarded to the application. So handling TCP state machine is done by the kernel, and after that is done, if it's a data packet, only if it is a data packet, then this data packet is enqueued into this read queue. Because we are talking about which side of the packet, we are talking about the received packet. So this packet is enqueued in the read queue. Again, next question. Do we enqueue the packet in the read queue or a pointer in the read queue? So the answer to this is you just enqueue the pointer. And when I say pointer, I mean the escape of struct. So note, there is no copy made for a packet within the kernel by the CPU. There is only one copy for the entire processing, which is DMA'd from the NIC into the kernel. No other copies are made. So the read queue, you enqueue the escape of saying that इस socket के लिए एक packet receive हुआ है. And I'm sure you are aware that when you write your client program, after creating a socket, you must have written something like a read sys call for reading the packets. So this read sys call, right now let me assume it that it's a blocking read sys call, where this read sys call, after executing, it keeps listening if a new packet has arrived. So what is it actually listening to is, it's listening कि इस read queue में कुछ data आया है कि नहीं. And so once this packet is enqueued into the read queue, the socket is signaled saying that a new packet has arrived. This is how the blocking read system call works. So now the application knows the new packet has arrived. Now when the application comes to know, the application runs in user space, you will have to switch back on socket read from user space to the kernel space. And after switching back, what do you do? Now, application cannot access this memory. Who can have access to this packet buffer memory? Only the kernel and the NIC. So which includes the driver also. So only they have access to this memory. So this particular memory cannot be accessible. So this memory, this packet buffer is now copied. This packet is copied into the application space. So this is the first time the copy happens, and this is that mem copy that you do. So this is involving CPU. So copy the packet, and after copying this packet, once application has received it, is escape buff का कोई फायदा है नहीं. So we will release this escape buff, provided nobody else is accessing this packet. If somebody else is accessing, we have to remove it still, because you remember कि writes cannot happen on this packet. So we'll have to release it, but we'll also have to unlink the other processes who are accessing it. And then return back to the application. Return back to application means you will be moving back from kernel space to the user space. And that means your receive process is over. So this was the entire path from packet coming to the NIC up to the receiving up to the application. Now let us look at the reverse path, which is the transmit path. So here an application has created a packet. After creating a packet, the application will make a write sys call on this socket, and since it's a sys call, you will move from user space to kernel space. The application will just specify the addresses. This kernel will copy the memory from this location into the packet buffer. Only one copy, done. And after this, it's the job of the network stack to handle sending this packet. So on socket write, packet is written, and socket's send function is called. That is something like a send message. And now the first thing, as you already told me in the first slide, now processing will happen from application layer towards the physical layer. So the L4 processing starts. So you have pushed the data in the packet buffer, but there is nobody who knows about this location. So we need a pointer which maps this packet, a structure which maps this packet, and we'll use that structure throughout. And what is that structure? So SK buff. So L4 processing mein an SK buff is allocated for this, and now we'll use a write queue. You're writing a packet out. So this SK buff is enqueued into the write queue, and after this L4 processing is done, L4 specific processing is done, layer 3 processing is called. So some common processing which both layer 3 and layer 4 does are creating a header, adding that header to the packet buffer. So application packet header nahi lagata typically. So all these headers are built up by the kernel in the network stack processing, adding the header to the packet buffer, updating the SK buff pointers, all of that is done as a common process. And layer 3 checks if there is some fragmentation needed. These are some typical things that you studied in your Linux computer networks course. And the L2 protocol handler is called. Now there is something new. What do we have now? We have a structure here in the kernel, in the write queue. We have the packet stored here. What's the objective? Send this packet out on the NIC. So out करने के लिए पहले तो this packet information also has to be added to the RX descriptors. Data was copied the first time when you made a send message call. First thing is for directly copied, directly via syscall, via the send syscall. Packet buffer is managed by the kernel and the NIC, that driver and the NIC. So what happens is when you make a write syscall, that write syscall will invoke, the syscall routines, and this syscall routine basically calls the driver routine, and this driver routine will copy. Yes. Then it will mem copy it from the application space, the user space, into the packet memory. No, that's what I'm saying. Nothing added. It's plain data with the gray portion on the empty portion on the left, empty portion on the right. Just plain data is pushed into the memory, device memory. And after that data is just pushed, after that the allocation of SK buff happens, because till now there was no SK buff. So next is SK buff allocation, and after that only you will add headers. So who adds the headers is not the application, it is the kernel.
But in this case, when we are adding headers, though we have empty space, right? But every time adding any, we have to shift the bytes and all.
No, you don't shift, right? Because there were two parts, right? Empty space on the right. So I'm using the word empty space. There is something called as a head area and the tail area. So whenever you make insertions, you will start making insertions. So firstly, okay, there is some complex structure which I have hidden. So, okay, I have just hidden the slide because I didn't want complexity, but this is how, I hope I'm not interrupting the flow here, but so you see after allocation of SK buff, there is a tail room that is allocated, and there is some process called as a reserve SK buff, and that will create a headroom. So now you have a headroom and a tail room. So whenever you add any data, so like first thing is you add data. So that data is appended after the headroom. So, and then now whenever you want to add something more at the end, you use SK buff put, that is after the data area, and you use SK buff push for before the data area. There's some complicated routines that exist here. Yeah. L3 processing is all done, where now next step is during layer 2 processing, that means who will be involved now? You will have the involvement of the NIC driver now. Yeah. So for L2 processing, NIC driver will be involved. Job is, what's the job? Currently, data is pointed in the write queue, data is present in the packet buffer. Now we also want to push that data into the, into the TX ring buffer. So that's the job of the network driver. But before that, the driver does some more things also. So let's understand that. So there is something called as a Q disk. You will learn this during the hands-on session also. So before you want to send out the packet, what if you want to apply prioritization to the packets? You want to do some kind of packet scheduling before pushing the packets out. So if you want to do something like that, there is a routine called as a Q disk routine. The job of this Q discipline is to apply priorities. So what does it do? There is a Q disk queue maintained in the kernel, and its job is to hold the packets in the queue and apply the scheduling policies. So there are some predefined policies that exist in the kernel, FIFO, priority queuing. If you want to add more policies, you can do so by changing the kernel, but there are some well set of policies that exist there. What does QDisk do now? After the writes is called, we have recognized that this data is ready, and because data is ready matlab, it's available in the packet memory, in the packet buffer. So now QDisk will pull this escape from here and make a copy of it into the QDisk queue. So now this QDisk, the escape is here and it's pointing to the packet memory. Remove this escape from the write queue. That is basically you will dequeue it from the write queue. It's not deallocated, it is just dequeued. Escape still exists here. And after that, does the post-processing things like calculating IP checksum, TCP checksum, all of that cannot be done by the hardware. It has to be done by the kernel for now. Let's consider for now that this checksum calculation is done by the kernel. So these calculations are done. Anything that hardware cannot do, everything has to be done here by QDisk. And after this processing, post-processing is done, the NIC driver send function is called. Now, what happens during the NIC driver send function is, yeah.
So here, the QDisk essentially again points to escape of, like uses escape to point to the property packet, right? It doesn't contain any copy of it.
It does not contain any copy.
But it decides like which packet to send based on what queue discipline is used.
Yes. So write queue is per socket queue, and QDisk is a global queue for that NIC, where we are ready to send data. Okay, so now data is ready to send. So next thing is the NIC driver checks that is the hardware queue ready or not. That means we are talking about which queue now? Those TX and RX descriptors now. So now we are sending it. So we are talking about the TX ring buffer. So is there space or not? That's what is checked. If there is enough space, if there is not enough space, you will have to halt here. The QDisk queue will halt. Otherwise, the job of QDisk, the NIC driver is now, NIC driver has access to that memory, right? So NIC driver's job is to map this packet data for DMA purposes. So DMA को बताना पड़ेगा starting address क्या है, ending starting address, source address क्या है, destination address क्या है, and length. So that information is passed on, and after that information is passed on implies that in this buffer, in this descriptor, an entry is made. After this, tell the NIC to send the packet. Now what does a NIC do? So anything that is to be done on the hardware, now we are talking about that. So I told you checksum offload hota hai. So now I'm talking about Ethernet checksum. So Ethernet checksum calculation is done, and the checksum is appended to your packet data. Where is it appended? It is appended in the packet buffer, जो तुम्हारा right side वाला room था उसमें. And after appending that, an interrupt is sent saying that the packet is sent. So interrupt is sent. Before that, in between this, what exactly, when I say send packet to wire, what exactly has happened? There is a DMA operation that has happened. We have invoked the DMA and told ki data bhej do. After this is done, interrupt is sent to the user space that your packet has been successfully sent out. And only after this interrupt is sent, this escape buff is released. Till then the escape buff is not released. And then you will proceed with the next packet in the QDisk queue. So this way we have now completed the entire path on the transmit side. So we have the receive and the transmit process done. I did talk about one packet. Now, any questions? Yes. Side effect of context switching, whatever cache locality you built up is all lost. So your cache gets polluted, which again degrades the performance. There is per packet interrupt that we talked about. Every packet comes in, hardware is saying stop doing everything. So that is what I talked about is vanilla Linux system. So अभी तक मैंने जो भी whatever I have talked about till now is all about vanilla Linux systems. But reality में vanilla Linux system, we are not talking about that. I mean, we are not using it today. So today, the first optimization that every system has is instead of handling per packet interrupts, it handles interrupts of a batch of packets. And this new concept, I think this is called as NAPI, N-A-P-I, new API. And this, I think, is started from 2007 or before that. So because of that, per packet interrupt processing doesn't happen. But per packet interrupt processing doesn't happen, but per packet processing does happen. But interrupt is handled at once. The other problem is dynamic allocation and deallocation of your escape up structure. That is also going to add overheads. And another overhead is copying the same packet from the kernel space memory into the user space memory. And the last one, but not least very important, there are some shared data structures between multiple processes running in the kernel. So we are talking about the packet moves from one module to the other module, but there are many modules which are using these common data structures. For example, I did talk about the RX and TX queues in the user space, socket queues. So socket queue जो है, for multiple packets, this socket queue will be used. So if one CPU is processing one packet from this queue, and you have multi-core CPUs today, speed up करने के लिए तुमने बोला कि एक packet यहाँ से ये CPU ले लेगा, दूसरा packet second CPU can pick up and work on it. But both the CPUs will have to access this common set of queues. And hence that becomes what you'll have to do, you have to have an atomic operation there because they're handling common data structure. So you'll have to lock, unlock. So locking and unlocking also adds to the overheads. So there are many overheads that exist in packet processing in your Linux kernel. So the takeaway from this slide is that we need to do something about it. This kind of Linux system cannot work for our server because we are talking about the server Linux operating system. So handling this 400 gigs or 100 gigs is not possible with this kind of a system. But this is good enough for your local laptops and all. There is no need to do anything about it because you may not even go to a Gbps speed. So you don't need any optimizations there. Okay. So I think this is the same thing that I'm talking about here, that what are the different sources of overhead, mode, context switching, locking, unlocking, packet copying, and so on. Yeah. So now let's move ahead. So I finished up the first part. That was about how the Linux networking subsystem works. Now let's go to the next part. How the NICs have evolved over a period? What has happened? So till now, whatever I've discussed, there was one offload, one thing that was offloaded to the hardware. When I say offload, I'm saying the task was assigned to the hardware. So which task was assigned till now? Ethernet checksum calculations, even Ethernet checksum appending. So checking as verification as well as appending, both jobs were offloaded. And there are many other offloads that are available in modern NICs today. But before even going to the offloads, let's understand why do we need offloads. So first thing I already told you, your laptops don't need these offloads at all. A regular Linux network stack is good enough to process up to 10 Gbps speeds. You don't need to do anything more. So where do we need these offloads? Where you are processing high speeds, typically within a data center or in the cloud. Why do we need them? Number one, so just to give you a brief idea, I think you can see here. Yeah. So you can see here that if you want to process 100 Gbps of data rate, just simple network processing, TCP packet accept करने और भेजने, that's it. Just to do that, you will need 20 CPUs for 100 Gbps traffic on the receive side and 10 CPUs for transmitting this. Application processing is not counted at all. It's just packet processing. Typically, server के पास कितने CPUs होंगे? I mean, even if there are huge servers, you have 64 cores, 128 cores, something like that, but not more than that. So if we consider a 64 core server, 30 CPUs are lost only in processing packets, just taking and receiving and sending out packets.
So one question, why RX is having twice more CPU than the VX?
So when we saw the RX path, right, it has to do a lot of, so it was compute intensive with respect to the tasks that it was doing. Like for example, so if we look at the tasks, right, one is you have to check the checksums and everything at each layer, and you have to do the fragmentation, you have to coalesce the packets, keep waiting for the packets to come back. So there's a lot of processing compared to the TX path, because no errors, nothing is there, you don't have to do error handling and stuff. So computation heavy component is the RX path. Okay, yeah, so the point here is one thing, as I said, 50%, 40 to 50% of CPUs, if you're using it only for packet processing, where will you run your application? So you need to free up the CPU cycles for application processing. So that's the one intention of these hyperscalers, that is I'm talking about the cloud here. Second, because it's a network packet, it is possible to do some specialized processing on hardware. Hardware is typically a good idea if you want to do specialized processing. Hardware is not a good idea for generic processing. So generic processing ke liye your CPUs are good, your general purpose CPUs are good. But with network packets, you have a lot of specialized processing that you want, so it's good to offload it. The third point here is with these offloads, you will scale the performance. So what I mean is, you will improve throughputs and reduce latencies, which is important. And the most important thing that the cloud providers or anybody in the business cares about is saving money. So offloading to hardware reduces CPU utilization, reduces power requirement, so it reduces the costs in both the ways. That means the operating costs as well as the initial costs for the infrastructure procurement itself. So because of this, we want NIC offloads. And how have the NIC evolved over a period? So there are a few basic offloads. Okay, I think before I go to the answers, let me ask questions. What do you think after listening to all of this, that why you should do offloads? What do you think after listening to the entire journey of a packet? What can be done to improve the processing? Again, reframing the question, what component do you think we should ask the hardware to do in a typical network packet processing so that we release that processing from the general purpose CPU? Checksum, yes. So checksum specifically for Ethernet is compute intensive. Even for IP and TCP, checksum calculation is not, it's a one complement method, I think, if everybody is aware of. Ethernet uses CRC mechanism, and IP and TCP uses a one complement method for checksum calculation. So it's compute intensive. You would want to even offload the IP and TCP checksum calculation to the NIC. So yes, so idea number one, anything that is compute intensive, offload it. Anything else? Why are these overheads happening? Because of per packet processing. Can you tell me something about it? What can we do? Yes. So the question is, can we reduce the number of packets that we are sending without changing the intent? What does this mean? Application wants to send a 10 GB file. If it wants to send a 10 GB file, it cannot send 10 GB at once. I mean, why? Okay, let's not say 10 GB. Let me say 100 MB. Memory में तो fit हो जाएगी. 100 MB file, still I cannot send it in one packet. Can you tell me why? Because of the MTU size. Your network will have an MTU. So maximum transfer unit, that is, there is a limit on how much data can be packed in a single packet. So for Ethernet, if you guys are aware, the MTU size is 1500 bytes. So then the application will generate maybe smaller size packets, and for every packet you will go through this overhead. So one way to reduce this overhead is, instead of sending smaller size packets, wait till the end to break down this packet into smaller sizes. Wait till the end मतलब कहाँ पे problem है? Wire पे भेजने पे problem है. The Ethernet allows only 1500. So before you push this onto the wire, can you take a bigger size packet and divide it and then send? And that can be offloaded to the NIC hardware. This concept is called as segmentation offload. So this process of dividing this packet into smaller segments of MTU size packets, this is called as segmentation, and this would reduce the load on the CPUs. Because a bada packet है, एक ही processing करनी है instead of 100 times processing. Can we do the reverse also? So on the reverse side, when you receive a packet, what size packet you will receive? Maximum size of the packet will be MTU size. So if you process the packet as soon as it arrives into your packet buffer, you will have to invest for each packet that is received. What can you do instead is combine multiple such packets that belong to a single application into one big buffer and then send it at once to do the entire processing at once up to the application. This concept is called as receive offload. So we talked about transmit offload, which was segmentation offload. There is receive offload. इसके भी varieties है. So when I say offload, in networking there are software offloads as well as hardware offloads. So when I say, okay, I hope I'm not confusing. Hardware offload, when I say, that means this computation is done on the NIC hardware. When I say software offload, I'm doing this processing in the kernel instead of user space, or somewhere closer, somewhere towards the end of the kernel. Before, for example, I'm talking about segmentation offload. Instead of TCP doing the segmentation or IP doing the segmentation, I will do it at the driver level before sending it out. So that is a software offload. Okay, so I talked about two things. I think the first 2 points you can see. The basic offloads mein you have, as I said, if there is anything, any computation which is required at high frequency, and if it's compute intensive workload and it is specialized for packet processing, you can offload it. An example is your checksum offload. If I want to just give you some more insights, are you open to listen to new things, or is it becoming too much? Okay, so if I want to give you some more insights on this, there are two types of checksum offloads: generic offload and protocol based offload. So till now whatever I said, right, हमें पता होगा कि TCP है, तो TCP के लिए ये offload mechanism है. You know that TCP header, where does it start, where does it end? IP के लिए you know where does the IP header start, where does it end. So that is protocol specific checksum offload. But today in data centers and the cloud, typical packets are never sent. Packets use different encapsulation techniques. Because of virtualization, packets are hidden within hidden or encapsulated into some other protocols. So typical packets don't exist. So you may want a technique where I just want to tell the hardware, don't worry about the protocol. The data for which checksum should start is starting at this point. That data is ending at this point. That means length बताना है. या नहीं बताया तो भी चलेगा क्योंकि start पता है तो end तक लेना है packet को. It is starting at this point and the place where you have to put the checksum is at this point. दो offset बता दो and the hardware will just does not have to worry कि ABC protocol है, XYZ protocol है. It will do the checksum calculation and put the checksum. So this is a generic mechanism. It's called as generic segmentation offload. So generic segmentation offload भी है, generic checksum offload भी है. So that is about the first way of improving performance. Second, we did talk about segmentation offload, increase the packet sizes on both receive side as well as sending side. The third component, this one. How can we further improve performance? Everybody knows parallel processing. So can you tell me so when I say parallel processing, from where does the processing start? From the driver end. When the packet is put in the device, in the RAM, in the packet memory, and the packet arrives at the transmit or receive queues, arrives at the receive queues. If I want to parallelize this, what can I do? अगर एक ही queue है मेरे पास, तो एक ही DMA उस पे processing कर सकता है. Otherwise, there will be locking, unlocking concept, and that will completely degrade the performance. In hardware, you don't want to do all of that. So the next idea is, can we have multiple DMAs that run in parallel, and each DMA has its own queue, and so each DMA picks the data from separate queues and feeds it to does the rest of the processing. So that is another parallel processing that can happen, and that concept is called as the multi-queue concept. So today modern NICs have multiple queues in the hardware. I'm not going to the details, but I'll be sharing a link that you can go through to understand that how this multi-queue on the transmit side and on the receive side can be designed and how it improves performance. So yeah, till now we talked about basic offloads, and mostly if you go for a medium-sized NIC, they will have all these offload functionalities. Now let's go to the advanced offload mechanism. Before I get into this, when we talk about any networking algorithm, there are two components in that networking algorithm, the data plane and the control plane. So let's take the simplest example which everybody is aware of, routing. So if we talk about any routing algorithm, BGP, yes. LSR, yes. So link state routing, border gateway protocol, these are some routing protocols. So what does any routing protocol, routing is what? Directing the packet. So what exactly you do? Packet comes in, you look up into a hash table, check, match for some keys, and take a decision where to send it. So there are two components. Number one, this matching and sending component, and the other component, somebody has to fill these routing tables. And that somebody who fills these routing tables will use some algorithm for decision making on how routing happens. So that decision making algorithm is the control plane, and typically control plane runs in software. And this match action processing, what is match action processing? Packet आया, key match करी, hash table में lookup करी, you take this action and forward the packet. So this forwarding is typically a very fast process. It should be a fast process, and it has got not much of complexity. This component of forwarding is called as data plane. So hardware के लिए what is a better idea if you want to do an offload? As I said, complicated चीजें hardware पे नहीं डालनी है, simplified चीजें डालो. So typically control plane processing is never offloaded, data plane processing is offloaded to the NICs, to the hardware. So, and there are many more reasons. One thing is complexity, the other thing is the control plane algorithm that you have devised. Typically it changes, and if the algorithm changes, usko wapas you have to again reprogram it for the hardware, and that reprogramming curve is very steep. So typically you don't want to do complex processing on the hardware. So yeah, so now moving on to the advanced offloads. So as I said, data plane is what is offloaded to the hardware. In this particular example, there is a use case considered for one of the complicated process, which is encryption decryption process, the crypto process. So let's consider a scenario. So let's come back to our original picture. You had your edge, right? You have your edge, you have your CDNs, and all the traffic would be entering these edge or CDN networks. And I'm sure everybody is aware this packet is encrypted using TLS protocol. So there will be a gateway at this edge or CDNs, and this gateway's job is to end this TLS tunnel here itself. So there is a tunnel between the client, an encrypted tunnel between the client and this edge gateway. The traffic from the edge gateway inside this network could be in plain text format. Could be. If you want to implement security there, then the job of this gateway is to stop this tunnel here and restart a new tunnel within the CDN network. This is what you will study. I mean, the reason of this you will study in the hands-on session when you talk about load balancers and stuff like that. So typically, if I have a server running within the CDN, just a simple question. There is a server running within this CDN. When you are requesting some service from the server, do you think that the IP address that you get from the server, for this particular server, is actual IP address of the server? No. Okay, simple example. If you are pinging, let's say a Google machine, you're making a Google request, a web request. How can you know what is the IP address of the Google server? Okay, DNS, but command line से देखना है तो कैसे करोगे? Simplest thing. हाँ? NS lookup भी थोड़ा complicated है, but for everybody else, pinging करोगे, ping करोगे, you do google.co.in or google.com, you will just see the IP address of that Google server. So do you expect that that IP address that you're seeing is actually Google server ka IP address? No. So Google server will be residing behind a gateway, and there will not be one instance, there will be multiple instances of this Google servers. The IP address that is visible to you is the IP address of this particular device, and this device will load balance among the actual instances of the server. So ये IP address तुमको दिखता है, hence और ये IP address पे ही तुम्हारा TLS connection break हो जाएगा. Internally, if you want to keep the traffic encrypted, you can do that, but otherwise not. So coming back to the point, the amount of traffic that this gateway has to decrypt, this gateway or the CDN gateway that we are talking about, the amount of traffic is huge. And if we leave this processing to the CPUs, it's a lot of CPU processing spent only in TLS packet processing and not actual application processing. So this is one very important use case for data plane offload in hardware. So there's one example of one of the SmartNIC that is shown over here. The Innova solution, which is offloading IPsec solution. IPsec is again a security tunnel that it's a protocol for secure communication between two private networks that you can have. So this is again is compute intensive operation. So these guys have prepared a solution for IPsec. And it's a fixed function solution. Fixed function ka matlab kya? The code is written, the hardware is created, and that hardware is pushed on this NIC motherboard, done. Tomorrow I want to change IPsec, I cannot change it. It's fixed function. But, and this fixed function solutions are typically called as ASIC solutions. The thing is here that tomorrow you can't change this, and if you want to change it, the cycle, the time required for the change to happen is in the order of years. So typically, ये कब use करा जाता है? When you are sure that at least for next 10-20 years, nothing is going to change. So typically, like AES protocol, we knew for a very long time that it's not going to change, it's secure. Now we think that in few years it might need a change, but for a very long time there was no need to change. Okay, can anybody tell me why we may need a change in the AES protocol? Huh? Quantum systems, yes. So because of that, there could be a need that we might have to switch over. But for a very long time, AES was stable and we knew it's not going to change, so it was already baked into the ASICs. Okay, so this particular solution, I mean, it was giving you some benefits of 10 times CPU savings and 6 times of throughput improvements. But, and now what do we do then? Like, if your solutions keep changing, right? Not so frequently, not daily basis, but they change in 1 or 2 years. Then you would want your solution to be more flexible, your hardware offload solution to be more flexible, where the programming can be done. You want a programmable hardware. So the next set of advanced offload schemes that started sometime after some 2016 onwards, or the actual thinking was started in 2010, and the development started sometime in 2016 and all, where the network card itself is programmable. You can write your C programs or some high-level language programs and feed them onto these hardware. It's not that simple, but I'm just making it look simple right now. But you write those programs in high-level language and push them onto this hardware, and they will start working as per custom design that you mentioned. So the turnaround time is not in the order of few years. It could be few months or days, depending on your programming skills. So now I'm talking about not fixed function hardware, programmable hardware. So there are 3 main categories of these programmable hardware. The first category is NPUs, called as network processing units. Now, the structure of this hardware is there are multiple cores similar to your system. In your system, you may have 8 core, 16 core, in servers it's 64 core. But on these hardwares, you will have like 400 cores, 500 CPU cores. And these 400, 500 CPU cores, they are not general purpose, they are domain specific. So here domain specific ka matlab kya? What is the domain that we are talking about? Networking. So these CPUs are specially designed to process packets. So there is some general purpose tasks that you can do, but mostly it's specialized for packet processing. And it works like a multi-threaded architecture works. So that is one category of processors or offloads. The second category of offloads is where you have FPGA fabric on your smart NICs. So what is a smart NIC? A network card which can be programmed. So on the FPGA based smart NICs, you can do gate level processing. So when I'm talking gate level, there are logic gates on this FPGA fabric. So AND gates and OR gates and all of that. You have memory ke liye, you can use these gates to build a memory, and you can use these gates to build a CPU and so on. So this is highly programmable mechanism where everything is flexible, but it's complex to program. The third category of programmable pipelines is general purpose processors. So there are these ARM processors that can be pushed on the network card itself. So for example, this particular smart NIC has got FPGA fabric as well as it has got 16 ARM processors. So if you want to do general purpose work, you do it on ARM processor. If you want to do network processing work, you can do it on the FPGA fabric. Now, I mean, I did talk about 3 categories, but what are the pluses and minuses here? I've told about 3 things. Can anybody help me out here? What will be the pros and cons across these 3 things? General purpose? Is the slowest. Okay, so that's a very good thread to start out with. So when you say general purpose processing is slowest, can somebody debate on it? Yeah. No, I want to debate on it on this particular parameter, that if we talk about a general purpose processor today, what frequency does it work at? 3 gigahertz and above, right? So general purpose processor works at 3 gigahertz and above, and your FPGA board or a SmartNIC board, that the NPU board, that has the frequency of megahertz. So when I say this is a frequency, what I actually mean is the clock time will be 1 by 3 gig here, and this will be 1 by whatever, if it's like 300 megahertz, and it will be 1 by 300 M. So frequency, if it is higher, the clock cycle is smaller, so you will do more instructions per second, process more instructions per second. So this is actually a very, very important point. So because there are a lot of misconceptions that people have, that hardware pe offload kara to it's always fast. So this misconception has to be clear. Can anybody help me out here? So now can you tell me, general purpose processor works at 3 gigahertz, your network card works at 300 megahertz. Who is faster, general purpose or FPGA?
You're saying that per instruction time, yes, but for computing, let's say, so by just in one cycle in FPGA, you will compute the entire function, whereas to execute that in a general purpose processor, you have to process a lot of instructions, right? So when you're programming on FPGA, you directly go like in one cycle.
Okay, that's one good point. Because you have customized instructions. In case of general purpose, you will have generic instructions. So a single component will require many instructions, a single processing thing. And on an FPGA, you will write a custom instruction, in the sense, a custom pipeline for doing the same thing.
The algorithm in the hardware itself creates, right? So in one cycle itself, you try the input in one cycle itself, you get out. Whereas in general purpose, like you are executing a lot of instructions plus minus and all, right? So that's why it's taking.
Okay. Yeah, so that is one point, but it may not still be completely correct. For example, if I do addition on the FPGA versus addition on the general purpose, I'm trying to come to one point. What you're saying is right. Custom instruction, you can have better processing speed on the FPGA. But one very important point here is, it completely depends on your algorithm. If your algorithm is sequential in nature, any hardware offload you do, it will never speed up. It will be rather giving you degradation of performance if it's offloaded on the hardware. So it's very important for the instruction that you are offloading to be highly parallelizable. So typically, to understand it very clearly, one simple example, GPUs are faster than CPUs. Can I say that statement? Depends, right? Now, again the same question comes in picture, right? Whether this program that you are running is of an SIMD type, where it's a single instruction, and it's the single instruction, multiple data streams are processing. I mean, you are processing multiple data items with the same instruction. It's faster on GPU, and it's a parallelizable workload. On the similar lines, FPGA पे भी processing तभी fast होगी, या hardware offload पे processing तभी fast होगी if the workload itself is friendly to parallelization. Otherwise, it's a good idea to keep your workload in running on the general purpose CPUs. And that is the very reason these SmartNICs are coming with 2 or more things on them. One is the FPGA fabric, second is the general purpose processor, There are also fixed function accelerators. So this single board has got your general purpose CPUs. They have FPGA fabric, plus they have fixed function accelerator. Fixed function matlab ASICs. ASICs are very fast because they're custom designed. FPGA, the speed is little lower than ASICs. CPUs, the speed depends on the algorithm that you run. So I talked about, because we're restricting ourselves to network processing. So I talked about there are two components in network processing, control plane and data plane. So control plane is more of an algorithmic structure which is going to be more sequential in nature. So the SmartNICs are designed such that your control plane will run on general purpose CPU and your data plane will be running on this hardware offloaded fabric. So I think this is one concept that needs to be clear here. And one more difference is whenever you decide ki offload karna hai, there is one important point, there cannot be any stalls in your computation. You can't wait for anything to come. You have to have your state before you start the processing. So stalls are not allowed. So stalls allowed hai only for one category of these data plane offload, which is the NPUs. Only for NPUs it's allowed, for others it is not allowed or not preferred. Because why for NPUs it's allowed? Because it's kind of a many core multi-threaded system. But वहाँ पे भी अगर stall हो गया तो performance is definitely going to degrade. So the point I want to say is two things. Number one, offload only things that are simple. Number two, offload only parallelizable algorithms. Number three is offload things where state is already available. You don't have to wait for the state to come. So these are the kind of use cases when you decide to offload an algorithm or not. I think the last 5 minutes I will just take this to finish this part. So we did talk about evolution of the NICs, starting from common offloads to specialized offloads to data plane offloads. Now how about the software end of it? Can we do something about the software end? So this was the typical kernel stack that we saw as the first part of the session. If I want to reduce the overheads, one of the options could be I can completely eliminate the kernel processing part. So network packet aaya, that network packet can be directly pushed into the user space. Then we will save on the processing at the kernel end. But obviously it's a good thing if you want to just take the raw packet and send it out. If you want to do TCP processing on it, then you'll have to build your own kernel stack here. So depending on the use case, this may be better if you don't want to run a TCP stack. Then this technique is called as a kernel bypass technique, and some of the popular solutions here are NetMap and DPDK. The alternative optimization could be, if you really don't want your application to read this data, or if you can shift your application such that data read karna hai, process karke bahar bhej dena. You don't want to do heavy duty processing. Then you can have your application running in the kernel itself. Take the packet that is coming in, process it within the kernel itself. You will save a lot of other things. After processing it, send it out. So considering the application is not a consumer of the data, it doesn't want to take and save the data, you can always do this kind of processing. So if you want to do some simple modifying and forwarding kind of application, you can just take the data, process it, forward it out. So you're going to study in this school, you'll be talking about, there is a session on eBPF where you will write applications that will be running within the kernel. So there is another optimization of that itself, which is called as XDP. So when I talk about eBPF, the application is running within the kernel. If I talk about XDP, even before the escape buff is created, I can do the processing just at the driver level. Before even the escape buff is created, send the packet out. So that's even better. And this again we have already talked about. Another alternative is don't even allow the packet to hit your driver. or you can process it directly within the NIC fabric, send it out, or even better, you remember the top of the rack switch? So when the packet hits that top of the rack switch, you can do the processing and send the packet out. So these are all sort of options available. Depending on the use case, you can decide what component of your application sits where.